introduction, and thanks everyone for coming and also for inviting me to speak here. And actually, I will be joining Seclé next year with a group of Eric. So I'm really looking forward to start, attending these seminars regularly and meeting all of you a bit more in person. So today I'm going to talk about this topic, which I did with Brian McPeak, who's a fellow postdoc with me in Pisa, and Ashish Kakar, who just graduated from University of Kentucky. So let me begin by just explaining why I got interested in this maybe not so common topic. So more broadly speaking, I'm kind of interested in questions under the umbrella of the bootstrap. So the bootstrap wants to study the space of CFTs. And this in general is still a hugely unknown space. So inside here, there is a smaller set of CFTs, which we have different reasons to exist, RG, arguments, etc. So there are some known CFTs, some unknown ones, and inside the known ones, there's a very small set of CFTs that we have solved. And the purpose of the bootstrap is to kind of expand these to smaller sets. So to start classifying and characterizing the different possibilities in the space of CFT, and also ultimately to expand this set of the CFTs to capture more theories. So what I'm going to talk about today is a setup where this picture is drastically simplified. So there are these code CFTs, which I will explain in detail what they are, and they form a much more rigid set. Okay, we draw that as some kind of rectangle. And even within the set, there is a section of theories that are not classified, not known. But then there is a portion of theories that are classified. And in fact, this has been the work of mathematicians in discrete mathematics or coding theory for a long time. And these theories are special. They are 2D CFTs, and they are lattice theories, so they're theories of free bosons compactified in lattices. And something remarkable about this class of theories is that even in the case, so you can do this at different central charge, and even in the case where the whole list is not known, it's known how to compute the average over this ensemble of theories. And you can write down, for any given central charge, you can write down what the average over the set of code CFTs would be. So one of the main points which I hope to reach you today is to explain how this average is going to be related to something that can be interpreted as a bulk partition function. So this would be 2D CFTs, so some 3D gravity or gravity-like partition function. And more, perhaps slightly more in detail. So this average is normalized sum over all codes. So each code CFT is labeled by code, and I'll explain what a code is. And then the partition function corresponding to each code, perhaps on some genus G Riemann surface. And then they have a natural measure, which is the inverse automorphism group of the code. And this sum turns out to be equal to sum over some gravity-like partition functions labeled by both geometries B. So, right, yeah. So here the boundary of B is this Riemann surface. Yeah.
Yeah, I was wondering what you mean by gravity line, because normally would like a large and large cap, you know, to have some sort of useful gravitation.
Yeah, so that's what I'm gonna try to study. So you can do this formula for any value of the central charge. So then the question is, when does the right-hand side look like a gravitational partition function? And kind of the end goal of today is to explain that for large central charge, there's emerges a large spectral gap and some other properties. So indeed, good. Right, so this was just the teaser. So let me explain to you what these error correcting codes are and how we can use them to construct CFTs. So that's the kind of main part I'm going to talk about, and then towards the end, indeed, I'm going to look at the gravitational properties of this average.
Sorry, what's this number in the front?
This is just essentially summing all these inverse powers up. It's a normalization constant. I mean, that's how we define an average, right?
Yeah, just, I mean, there are quotes in the writing this video equation, so I wasn't sure this was even necessary. But you're indicating that there's some normalization involved.
Yeah, you want to normalize so that the kind of vacuum contribution is like unit normalized. It's not important. Okay, so let me start with some more detail. So the main objects are binary error correcting codes, and I denote them C, and they're a collection of vectors, binary vectors of length n. And n here is an integer parameter which will be related or will be identical to the central charge of this CFT in the end. So a very simple example of such code is called the length 3 repetition code, and it just consists of two such vectors called code words. It's one with all zeros and one with all ones. So that's n equals 3 and two code words. And this code can be used to transmit messages over noisy channels. So if you have a message, a binary message, 0, you should encode it and transmit the 0 code word. 1, you should transmit the 1 code word. And then maybe there is some noise. So some of these bits might be flipped. And then we have some receiver over here. So receiving the 0 code word is being interpreted as 0. And then say that one of the bits gets flipped. So it's like 0, 0, 1, or the other permutations. We should still interpret this as the 0 code word. And likewise, 0, 1, 1, etc. goes to 1, and 1, 1, 1 goes to 1. So you just interpret the message as the nearest code word to the original start. And that means you can also try to get a measure on how good a code is, which is how many errors it can correct. So you see here, if you have 2 errors, then we don't correct it anymore. So this code is said to correct 1 error. And there's a formula for this, which is just floor of d minus 1 over 2 errors. Where this d is the minimum distance between 2 code words. So it's min b not equal to b prime of b minus b prime. So in this case, it's 3, so corrects one error. Is that clear?
So what you call a code is what is the collection of these vectors?
It's a collection of these vectors, yes. So far, I haven't demanded anything of this collection. It could be any collection.
But let me understand something. So in this, the code words are a subset of the possible vectors, right? So
Yes.
is the code the whole set of vectors, or
No, the code is exactly this subset. So
Okay.
in this code is really this set of two elements. And let me give you another example, actually. So this is the main example, which is the simplest code that's related to a CFT in the way in this construction I'm gonna describe. Main example called the Hamming 844 code. So this little triplet of numbers, it's not important for my talk, but it's some standard notation in this coding community. So this just means its length n equals 8. It has 2 to the 4 code words. So it needs to be a set of 16 vectors. And this says that this d equals 4, this Hamming distance. So again, it only corrects one error. So what are these code words?
So just is it something that comes from computer science or what?
Yeah. And actually, some of these error correcting codes are really used in practice for sending messages. For instance, I think the Voyager mission to Jupiter used not this code, but a slightly more refined code to send a message back to Earth. What?
To compress information.
Well, it's rather uncompressing, right? Because here you need to have 3 bits to send a 1-bit message, but it's to make sure your information is safe from corruption. Okay. So this is
In case of the change, you
exactly. So you introduce some noise, so you want to make sure that you can recover the original message with a certain amount of noise. And indeed, you want this distance d to be as large as possible, given the length of the code and the number of code words. So this guy consists of this, length 80 code word, has some other guys. And then it also has this or 1 code word. So there are 14 here in between. And they're all kind of distance 4 from each other or more. So that agrees with this d equals 4. And this code actually has some properties. It's called doubly even. That just means that each code word has a length divisible by 4. And it's self-dual. It's also linear. It has some different properties. I'm not going to go into the details about, and such codes are collected in what's called a type 2 code. And they are the building blocks for the construction of code CFDs.
You still need a mapping from these code words to the original bits, no?
Yeah. So here, So here you can imagine you would need you have 16 coders, right? So you can have some collection of 4 bits. To say the 0000 bit collection will be mapped to this one, and the 0001
Is it important, the ordering, or?
The ordering is not important.
It's not. It will not affect the result.
It will not affect the result. You just need to make sure the sender and the receiver agrees on the language. Good.
What does self-dual mean?
Self-dual means that if you take any such code word and multiply it with any other, and then take the result mod 2, you get 0. So this times that is 2, but that's mod 0. Mod 2 is 0. You can see it doesn't work for this guy. This times itself is 3, so it's not 0, mod 2. So this repetition code I'm not going to talk about anymore. Well, it's just my next equation. But okay. Apart from that, let me introduce an object associated to the code, which is called the enumerator polynomial. So it's an object that carries some information about the code, but not the complete information. For the complete information, you need to give this list. It's called W, indexed by the code, and it's the sum over the vectors in the code, x to the n minus v, y to the v. Absolute value v is the length of the vector. And x and y are auxiliary variables. So this polynomial for the two codes that we talked about, for the repetition code, is just x cubed plus y cubed. And for this, I didn't give it a name, I want to call it h. For this Hamming code, it's going to be x to the 8 plus 14 of these intermediate code words, x to the 4, y to the 4, plus y to the 8. So looking ahead a little bit, this enumerator polynomial will be directly related to the CFT partition function. But
This just keeps track of the code, the numbers of ones and zeros in each code word.
exactly. So it's a very kind of rough measure of the code in that sense. But you can get combined with this type of information, you can actually read off stuff like the Hamming distance from this. So the Hamming distance, this d, is actually the difference between this exponent and the next exponent in the next x power.
Can you give
So
an example
it's
on
useful.
Can you give an example on how to compute this WREP3, for example, for one of the code words above? Just I'm a bit confused about this x and y is what I mean.
Oh yeah, sorry. So yeah, so this rep3 is just it just consists of 0, 0, 0 and 1, 1, 1, right?
Oh, that's the old one. That's the old code.
Yeah, that's everything in this code. So you just have two terms in the sum. So the first term is x to the 3 minus the length of this guy, which is 0. So it's like x cubed times 1.
So it's just x to the number of 0 times y to the number of 1.
Yeah.
Just sum it.
Yes, and then the next one, the 101 guy, gives x to the 3 minus 3 and y to the 3.
Uh-huh.
So,
And WH is not the W for the code you have above. It's for a simplified code, right?
WH is for this guy.
Why is it for the full guy? I mean, why don't you get an x? Oh, it's only x to the 4. I see. Okay. I thought you got some x to the 6s also. Okay, no, thanks. I understand.
Yeah, I mean, I didn't give all of them, so you would be
No.
able to
I thought you
tell.
also had some guys with 6, but you only have guys with 4. Okay.
Okay. The next ingredients in this construction is a lattice that can be constructed from the code. So let's call it lambda sub c. It's a set of vectors. There's some normalization here for 2, but where this v belongs to the code mod 2, or equivalently sits into the code plus 2z to the n. So it's useful to draw some kind of picture here. This would be n equals 2, so a 2D picture. So the code itself consists of only zeros and ones. So it's a subset of the corners of a hypercube, or a square in this case. And then you construct the lattice by just adding integer, or rather two integers to these guys in all directions. And then there's the final rescaling. So the three players of the game is going to be the code with this numerator polynomial. It's going to be the lattice. And associated to lattice, you can write down something called the lattice theta function. Which is the sum of the vectors in the lattice q to the v squared over 2. And then for the CFT, the ingredients will be the partition function, which, well, I'll leave this open, and I'm going to derive what to put here for the CFT partition function. But before I do that, I want to make some remarks about the classification of the three types of objects we have seen.
I guess the code does not imply that they're all linearly independent. Oh no, they do, because n is the dimension of your lattice.
N is the dimension of the lattice, yes.
So the code structure implies that they are linearly independent as vector in a.
Yeah, you can do this for a linear code, which is again one of these specifications of the code that's worked on the road. Actually, you can probably do it for other codes too, but then it's not going to be a suitable lattice. Okay, so for the classification, I'm actually going to be very careful and specify the precise objects here. So the codes are these type 2 codes. There are other codes around, but these are the ones I'm focusing on today. The double even, self-dual, linear. Then we have even self-dual lattices. Oh, no, I don't. Gonna have space. Start here. Self-dual lattice. And then the type of CFTs are called meromorphic CFTs or one character CFTs. And they just have a chiral part, so CFTs with C bar equals 0 if you want. And all of these exist only for n divisible by 8. So the first case is n equals 8.
It's always a free boson on the torus divided by this lattice.
Yes.
Or before
No orbital folding, yeah, exactly. You can imagine different constructions from a lattice that take you to one CFT by the plane construction and another CFT by some orbit folding. But for now, considering the simple construction. So, okay, so at n equals 8, there is only one code. We have seen it. This is Hamming code. There is only one such even self-dual lattice. which is the E8 root lattice. And there's one CFT of this type, which is the, well, E8 theory, 8 bosons compactified on the E8 lattice. N equals 16, there are 2 codes, there are 2 lattices. There is E8 square, and that is called D16 or D16 plus, and there are 2 CFDs. E8 times E8 and SR32. So far it's very simple. Then we have N equals 24, where things start to become interesting. Here there are 9 codes of this type 2 codes. There are 24 evens out dual lattices by the work of Niemeyer. And there are 71 type C of the CFTs of this type. So this list includes the orbifold ones. So if you go from here with the construction I'm going to explain, you're going to land at a size 24 subset of these 71. So they are 71 by Shelokins. What's nice with these codes is that classification has gone further. N equals 32, for instance, there are 85 such codes. And the classification of lattices is not complete here. There are some estimates that you can derive. One says that there are more than 10 to the 7 such lattices. I saw a more refined estimate of 10 to the 9. And here on the CFT side, I haven't even seen any estimate of the number.
So how do you get more lattices than codes? Or the codes map to a subset of all these lattices?
Yes, exactly. So
Then what's the logic? Are you associating a CFT to the lattice or to the codes?
I would say, well, you can do both. For me, I'm associating it to the lattice. So by code CFT, I'm going to mean CFTs constructed just from this subset. So it's going to be, in the end, 9 out of the 71 possible CFTs at this site. And when I do the average, it's only going to be an average of the 9.
How do you get the 71 out of the 24?
Oh, I think most of them follow from the direct construction and some orbital construction. But I think there might be a few kind of more exotic ones in this list too. It was huge work to make this list, and I think it wasn't confirmed directly either.
But what determines this? I don't understand. You said it was just some boson compactified on this lattice. Then I should.
Well, no, some of them are boson compactified on the
all the
lattice.
folders.
So to do this list, you have to do a classification of chiral algebras. And I don't know the details of this part of the story.
Could you repeat, what's the definition of the furthest right columns?
Yeah. So the furthest right column, are CFTs that depend. They are purely holomorphic, so they only have holomorphic weights and satisfy a bunch of consistency conditions. They are modular invariant up to phases, and then to construct an actual CFT of them, you just take the chiral part with its complex conjugate, and then you get a full-fledged CFT. Whereas many other CFTs you know of is a sum of such pairings. So it's a one character, yeah. It's a one character theory. That's all. They go on their slightly different names in the literature. Yeah.
You don't need to pair left and right to get what I'd call a full-fledged CFT. It's just
Well, you can,
a special type of CFT.
Yeah, you can take the chiral part on its own and pretend it's a CFT, and that also works fine.
I don't think you have to pretend, though. It is a CFT.
Well, it's a chiral algebra, okay, it's a CFT, but yeah.
The special thing is that it's a chiral algebra with a modular invariant partition function. So it happens to be, it's a single character theory. The partition function is the character for the vacuum module of some special algebra. which happens to satisfy everything necessary to be a partition function.
But it's invariant only up to a phase.
Yeah, it's invariant only up to phase, yeah,
If you take c equals 24, then it's invariant.
and G as well. Yeah.
Yeah.
Okay,
And yeah, I mean, also to that point, if you just construct this partition function, it doesn't mean there is a CFT in the way that we like it with all the rest of it consistent. So the existence of a genus one partition function doesn't mean that the CFT exists. It also doesn't mean there's just one CFT with that partition function. It could be multiple.
No, but what do you mean that all the plane correlation functions are defined?
Well, here's just a matter of, degeneracies, right? I mean, that's.
so if you have, no, but if you have, if you know the lattice, then you know the CFT. If you know the genus one partition function, you don't.
Sure.
In fact, these two guys have the same genus one partition function.
Yeah.
But they are different CFTs.
If you're on the right, you're writing CFT, it's not the partition function.
I'm writing the CFT, full-fledged, it should be defined, all correlations should be defined, all genus G partition functions should be defined, etc.
But Schelikins just specify the partition functions. And the algebra is associated to them. So
Yeah,
there's a
but
little
if
bit
you
of-
look at the algebra and it's a free theory, then you know on the correlators and also high genus partition functions, in my
Right.
understanding.
Yeah, but sorry, I don't know if it means that something can't go wrong when you construct everything else. If
No, but they can be
give it-
different, as you just said, right? So the partition function at 100 coulomb will not know the difference between E8 square and E16. That's whereas they are different.
Yes, that's. That's what I'm trying to say, and just that when Schelikins wrote his paper, that 71 is a list of 71 partition functions and the associated affine algebras. But there could be some degeneracy in.
But then
CFTs.
at all genus or something, there's no way.
He just does genus one.
But I think,
But then
if
you
you- but if
not
you-
even distinguish E8.
but I think if you have the, no, but if you
That's
have
what I'm
the,
saying.
but if you have the chiral algebra, you should be able to compute more than just genus one partition.
Yes, I agree. You should be able to, but
Yeah.
he didn't do that. Yeah.
Yeah, but people have worked with his list after him.
I don't think it's proven that that's the full list of CFTs and that it's just.
I've seen some more recent paper discussing it and, saying this has been constructed there and this has been constructed there and.
But anyway,
Yeah.
maybe we should
Yeah.
not spend too much time.
There was another question there.
The center charge, so they're all.
They're all central charge equal this n. So this is central charge equal 24.
It's big recollection just from like another time that Witten was trying to construct the gravity partition function. But sometimes some people noticed some problem of going to n large. Can you remind me what the problem was or the different criteria? To some double maybe? There was some problem with, I don't know.
This was for the pure 3D graph.
Yeah, but
Yeah, I think you want to find extremal theories. Which in this list is one theory that's extreme and in that sense, like a monster.
because they're imposing a certain gap, whereas you're not.
Yeah, but then I think here the known list really ends. So yeah, let me just quickly finish this table. Just some more numbers. More question marks. Okay.
No, but I thought that in that case, it's not about known or not known, but it was a problem with existence.
So
But maybe you would say that nothing exists that has a certain.
no. There should be things existing here. If I try to guess what you're aiming at, but I don't know the story myself. If I try to guess what you're aiming at, is that they were looking for extremal theories. And you can play with the genus one partition function and try to extremize it, and then you find some solutions. And I think the problem is that you don't know if these solutions actually correspond to CFTs or not. And if you do this game at C equals 24, you're going to find the monster CFT, which actually exists. But further down the list, you have some candidates, but you have no way to see if they are actually consistent CFTs. We just.
They couldn't find a partition function, but I really don't remember.
I think it was higher genus that they analyzed. I mean, the genus one partition functions is sort of the only object that comes out of this game. And then there's a putative Q series, and it comes out of the game. And so the question is this a consistent CFT or not? And so the thing you can look at is, for example, genus 2 partition functions or correlation functions. But the correlation functions are kind of easily solved, the crossing equations, because they have a lot of states in these two series. Yeah,
Okay, so this list is supposed to go up to infinite n.
Yeah. But it's gonna grow in size very large. Even the codes grow in size, and after n equals 40, classification of codes is not done either. In principle, you just search the space, but the space to search is too big, so you need to do more refined things.
So, sorry, can you remind us why are we only considering multiples of 8 and multiple of 8?
From the code perspective, it's followed from these conditions, even doubly even self-dual code. In the CFT construction, it follows from invariance. There is some combination of modular transformations that is
It's the same.
it's the unique modular transformation, but the expression with the partition function can't transform to itself unless C is divided by 8.
So all of them read 0 for all the other.
Yeah.
A question?
Yeah.
It seems that if I give you the code, there is a unique lattice, correct? I mean, the construction for the lattice seems to be unique. So how do you get more lattices than codes?
There are some lattices that don't follow in this way. For instance, by doing this, you restrict lattices where you necessarily sit on these points. You can have lattices where you're like, I don't know, these type of positions too, which are also.
your classification is of even self-dual lattices.
Yes.
So that's an independent classification.
All of these are 3 independent classifications. Yes.
But they are not all, it's not a classification of even self-dual lattice, as you said, because it's incomplete, it's just some of the even self-dual.
No, this is the classification of
Yeah,
even
yeah.
self-dual lattice.
And
The 24, and the 9 are a subset of these 24. And here the classification ends, and there are only estimates beyond that. And the estimates grow quite quickly.
But actually, for self-dual lattice, I see the link directly with CFT, because clearly you start from that. You need an even self-dual lattice to define the partition function associated to a CFT. What is special about the code? What is the justification to be interested more in those few examples?
One motivation is that this list continues further. So you have simply more. If you want to start doing stuff like look like gravity, you maybe want to go to larger C, and here you have access to a bit higher in C. And another thing is that I would say that you don't need to do any work. If you have the code, you really have the partition function, all genus partition functions you can just write down straight away.
Okay, so you can know much more.
You can know much more about this, more restricted, of course, class of theories, but you can know much more about it.
But you mean in more practical, and because if I have the lattice in principle, I also know the genus rotation.
Yeah, but when you write about this, you need to
Yeah.
find a way to write the lattice. These codes you go in, there's some people who wrote a database of code. You can download the full list of all these codes, and you have them on your computer.
I suggest in advance.
Yeah, so now I need to cut a few ingredients slightly short, probably. Good. Let's keep this section. Okay, so let me just. So I think I should go through this anyway. So now we want to look at the torus partition function, genus 1 partition function of these guys. And so it in general takes the form the Latifica function over this modular discriminant that you can eta function of tau to the C. So just some quick notation. We have the torus, this kind of picture where this is a modular property tau, its Q is e to the 2 pi I tau. So you identify the opposite sides. And it's eta is e to the 1/24. One is Q to the n.
So you mean eta to the n, right? Not eta to the c into the.
Eta to the n, yes. Well, c equals n. The center equals n. So sorry, I was sloppy there. Okay, and
I see the central plot, not the code.
so now we want to evaluate this lattice theta function for lattice that comes from a code. So I gave you the definition before. It's a sum over vectors in the lattice q to the v square over 2. But then any vector in the lattice is a vector in the code plus 2z. So we can write this sum as a sum over vectors in the code now, and an inner sum k in z to the n, and q to the v over 2 plus k squared. Remember, there's an extra 1 square root of 2 in the lattice versus the code. And then if you try to organize this, you see that you're always going to have this sum over k. And what are you going to sum over depends on if the corresponding element in the code vector is 0 or 1. So you want to split this to keep as an outer sum the sum over code vectors. And then for some cases when there are zeros around, we're going to sum q to the k squared when this is 0. So here it would be number of zeros. And then when there is a 1 around, we're going to sum q to the k plus a half. So this number of zeros and number of ones in this vector v. Okay, these two guys are actually known functions with known modular properties. They're called Jacobi theta functions. Theta 3 of q squared and theta 2 of q squared. So we're going to have a sum over code vectors, which looks at each code vector and see how many zeros are there, how many ones are there. But that's exactly the definition of this enumerator polynomial we had before. This is going to be this enumerator polynomial, but now evaluated where this first variable x is the theta 3 and y is theta 2.
You can put genus G theta function and you get for free the.
Yes, exactly. So if the higher genus version, you're going to have a sum over pairs of code words at genus 2 or triples of code words at genus 3, and indeed they become the higher genus theta function. I'm not going to talk so much about higher genus. Well, we don't have much time anyway. So this is a very simple example that you can do. These theta functions are implemented in Mathematica. So if you just look at this E8 theory, which came from the Hamming code over eta to the 8, you get an expansion which looks like q to the 1/3, and then it's 1 plus 248 q plus more terms. So here you can see the number of currents in this theory. And if you've done some numerology, you recognize this number. Then this partition function needs to be modular invariant too. And there are some transformations called modular T and modular S. So T is just tau goes to tau plus 1. S is tau goes to minus 1 over tau. And there are properties of these theta functions. Well, theta 3 doesn't change. Theta 2 goes to I theta 2. And here under the modular S, theta 3 goes to theta 3 plus theta 2 over square root of 2. And then there's some little ugly extra factor. And theta 2 goes to theta 3 minus theta 2 over square root of 2. And then under this S transformation, there is also transformation for this Dedekind eta, which goes to minus I tau eta. That gets, since it sits in the denominator, it gets rid of these factors. So our partition function Z is modular invariant if this enumerator polynomial sitting up here satisfies the corresponding identities for its argument. So if W of xy equals W of xiy and also equals W of x plus y over square root of 2 x minus y over square root of 2. Now, if you want, you can take this expression that we had before, x to the 8 plus 14, x for y4 plus y to the 8, and see that it's indeed invariant under these. So now is the time to tell you that this relation between codes, lattices, and CFTs was completely worked out 1990 in the 1990s by Dolan, Goddard, and Montague, I don't know how to say his name. But these identities that we derive from modular invariance are known in the people working on error correcting codes by McWilliams. She wrote them down in 1963. And they have to be satisfied for any type 2 code. So this means that one way to do modular invariance or modular bootstrap limited to this class of code CFTs is to just solve these McWilliams identities and look for polynomial solutions with integer coefficients. So you can kind of do a toy modular bootstrap on code CFTs. And we investigated this in the first paper we wrote, and the second paper on some more general class of codes. And we wrote down these corresponding identities at higher genus, which were also, we found out, known by people in the code literature. And so then you have like a higher genus model of Bootstrap, which is quite cool. But I want to progress to the gravity slide in the last 10 minutes. Okay, I kept a secret for you that maybe will make it more motivated. Why another reason why you would study these code CFTs. It's actually that these building blocks, sorry, theta 3 over eta and theta 2 over eta are actually SU2 level 1 characters. So this implies that code CFTs are SU2 CFTs or SU2 to the C invariant CFTs. And we could speculate, we don't have a complete proof, but it's natural to assume that the set of code CFTs is actually equal to the set of SU2 to the C invariant CFTs with central charge C. So this brings me to the average. The average of a code was written down 1975, might be related then to an average over SU2 theories. And there is the formula for the average numerical polynomial, which is 1 plus 4 divided by 2 to the C over 2. Here's some normalization. X to the n plus y to the n plus 4 more terms. A equals 0 to 3. X plus I y over square root of 2 to the n. So again, if you want to do a little exercise to check that it's invariant under these transformations, because each member of the average is, so the average should be 2. You can also check, sorry, I want to put n here. You can also check if you put n equals 8, where there was only one member in the average, you're going to get back this numerical polynomial of the Hamming code.
So that sum runs over k up to 1 to 3.
K to, oh, sorry, I didn't write the k. It's I to the k. Yeah, or you can write all 4 terms separately.
It goes up to 3.
Yeah. It's like x plus y, x plus iy, x minus y, and x minus iy.
Sorry, what's the prefactor?
The prefactor is just so the coefficient of x to the n is 1, but it's 1 plus 4 over 2 to the n over 2. Okay.
These are how people prove this.
I don't like the proof. It's fine in the papers. It's kind of a bit, these are the only terms you can put, and then we fix the overall factor by demanding this consistency, and it's I don't think it's a nice proof. But it's correct. You can check it if you download this list of codes, you can just explicitly check it. Yeah. we have another way to arrive at this, which is what I'm going to explain now in the remaining 5 minutes. So,
But did you prove there were SU2C invariant? Because I understand that it's, I mean, you explain why you conjecture that, but it's clear that.
I don't know. I think it's almost coming to the level, what do you mean as a proof? Like, in a way, if you want to build a SU2 invariant partition function, you have to use these guys, right?
No, that, yeah.
And then they have to satisfy exactly the same properties as the code. So I don't see any way out. But
Sorry, the theory has a symmetry SU2 to the C, and C becomes large, and I expect a huge amount of degeneracy at low level. Because it's so much symmetry.
huge amount of.
Well,
You're gonna get many currents, right?
You have many currents, yeah. There were 200.
At the beginning of the talk, you said you're going to get larger gap.
Yes.
It sounded like a nice thing. So I'm a bit confused. How can you get a large gap with such a huge amount of symmetry?
You take this, okay, I'll give you this formula now, because it's in my notes. You take this guy. Okay, let's remember the recent idea. You take
Yeah,
this
very
guy,
good.
divide by E
yeah,
to
there is.
the C, you take the average. Theta 3, theta 2, you substitute the theta functions. And you read off the number of currents. That's one thing you can do. And the number of currents are 3C plus 8C, C minus 1, C minus 2, C minus 3 over 3 times 4 plus 2 to the C over 2. If you put C equals 8, you find 248. If you go to large C, it approaches 3C, which is the minimal number of currents you have to be SU2 to the C invariant. So all these kind of extra symmetry things become increasingly rare as you increase. And also you can look at the gap. And you can compute, and you see it goes as C over 36.3.
Sorry, how did you find that?
The gap in SU2 characters now. So you limit yourself to SU2 primaries, and you look at the next primary after the identity primary. And the gap in the average theory, so the average will have non-integer degeneracy, but they will be extremely small until some point where they suddenly become extremely large. And that's where you define the gap to be.
The currents are descendants of the identity, so you don't count them.
Yeah, you don't count. Yeah, they are SU2 descendants of the identity. These currents, exactly.
So basically, I have a theory that has a huge number of low-lying currents that scales with an N, which is.
Yeah.
But if I look at I don't know, if you do primaries, then the first non-trivial primary has a large gap.
Yes.
I mean, this is true for the average, right? But
in the average.
You don't know, right? Because there might be cancellations, like there might be low.
There can't be cancellations because it's all the weights are positive, but there will be exceptions. Okay. For instance, you can just take E8 to the C over 8. That's going to be one theory. It's going to have many more currents than this guy. But just from the average formula, you can see that it's just one member of a hugely expanding class. And it becomes washed out in the average.
So if I try to compute the correlation functions of these primaries, would the currents affect larger factorization?
Well, you have to make sure what you mean when you say
in the average theory, yes.
A primary in the average theory, because it might not. The primary you want to look at might not exist in all members of the average. We haven't explored this too much, but it's something I want to look more at.
So I didn't quite understand the splitting into characters. SU2, you mean the diagonal SU2 or of these C copies?
The kind of chiral, this C part. These are all chiral theories anyway, so.
No, but you have many.
No, but there are many SU2 factors, right? There's N of them. So you mean and that's probably the full chiral algebra already, so.
Yes, so the full chiral algebra is SU2 to the C.
So there's just one primary, which is the identity. So then what is this subgrouping that you're mentioning? Is it with respect to the diagonal of SU2?
That's all.
Well, the characters of like a direct product is simple products of the characters of the member. This is K equals 1.
So one of your claims is wrong, because you're saying there's a single primary for this SU2 to the C. I think that's not consistent with what's.
No, it's a single primary over an even larger symmetry, like a discrete symmetry, like this corresponding lattice symmetry. And then in turn, there are different primaries. And this E8 guy is a single primary over the E8 chiral algebra, but a sum of primaries of the SU2 to the 8. Okay, now that's fine, but I still want to write down the final equation. So the final equation is the gravity interpretation, which says that the average partition function, the sum over some object that has an interpretation of about geometry, some corresponding partition function. Okay, so let's look at genus 1. Now, there's a similar formula to genus. And then some pretty generic feature that happens in 3D gravity is that such a sum over both geometry is B. So again, the boundary of B is the torus. Just the sum can be written as sum over some subset of modular maps, set B0 of gamma tau. So here set B0 is one particular bulk geometry, and it's kind of the vacuum geometry. If you take your torus and you kind of fill it inwards and evaluate the gravity partition function on this. This is the kind of chiral gravity. There are different versions of this formula. In our case, we don't even really know what the bulk theory is. It's some kind of exotic SU2 Chern-Simons theory with emergent gravity. But that's again an open direction to really write this down formally.
I mean, I don't know if it's a theory of chiral gravity. There are some proposals based on PMG, but that's kind of okay, fine.
Yeah. So okay, so since we're in the Henri Poincaré Institute, this such a series is called a Poincaré series. And in general, it's an infinite sum, but and this will be my final point today, that in our code CFTs or SU2 CFTs, this sum of modular images is actually finite. It has 6 terms, and if you compute it, so you're supposed to start from one term, set B0, which is kind of the vacuum of your chiral algebra, which is this x to the n. Then you take these modular transformations, which are these Williams identities. Say the first thing you're going to get is x plus y over square root of 2 to the n, and then you apply s and t iteratively until you exhausted all combinations. You're going to find 6 independent terms, and these are exactly these terms. So now we give kind of a gravity interpretation of this ancient average formula. And we can do this at higher genus too. And
sorry, how do you argue from very? I guess you say that you must have t-test 3 to the n divided by n, and I'm not trying to understand why you could start from that.
In these other examples, like U1 to the C, this work by on average of a Narayan moduli space, they do start from the U1 to the C vacuum character in the Poincaré series. And same in an attempt of 3D gravity that still has many problems, they would start from the Virasoro vacuum character. So we just assume that you should start from the SU2 to the C vacuum character. which is 3 to the n over eta to the n, or translating back to the code language is x to the n. And well, we tried, and it gave exactly the known average formula.
That instant we could by, the what I said, we'll do that by construction, of course, it construct the polynomial one by one, right? But just the intuition why this SU2 vacuum character is the right thing for on the gravity side, I'm not sure I understand if you have a way to give an intuition of that.
I would say my personal intuition is not much more than analogy with the other cases. In the kind of pure 3D gravity, people, there's work by Dijkgraaf, Malacena, and some other people from early 2000s, where they tried to classify bulk geometries and equivalently classifying ways of building geometries that have boundary the torus. And one of these terms is when you just fill the torus inwards, and you can compute some point approximation of the gravity action there. The leading term is almost the Virasor vacuum character, and then there is some kind of value computation, which gives in the end the whole Virasor vacuum character for this geometry. And then there's an independent argument why the sum over all geometries can be written as a sum over modular images of one particular geometry. And this has to do with like a geometric way of building bulk geometries. Some of these are like Euclidean versions of the BTC black hole. And it turns out that you can, yeah, you can all relate them to a modular image. And the reason is that they are actually parameterized by a larger space, like a cover of the moduli space, Schottky space. And but then the boundary geometry only knows about the projection down to the modular parameter, and therefore you need to sum over all geometries that projects onto this boundary.
Right, because the geometry only depend anyway on tau modulo SL2Z, but you say that the uplift, I mean, you define the vibration through
yeah, if you want the bulk partition function only depends on the boundary modular parameter, but not valued on the moduli space, valued on some larger covering space. So this sum is the sum over all images that project onto the moduli space for the modular parameter of the torus. I think we're out of time, so I'm going to stop here. I wrote down the final formula, and I'm very happy to finish here.
let's thank Johan.
Questions? A quick question. Is there a relevance for the Golay code in your analysis? Like the Golay code has some special properties, so
yes,
let's give a particular.
Yes, the Golay code. So there was this list 1 to 9. The Golay code is one of the 9. It maps onto one of the 24. But it doesn't land on an interesting one, on an interesting lattice. But there's another construction, like our construction is called construction A, but there's another construction like a twisted construction, which means the Golay code, well, twisted? Oh, it's another construction that makes the Golay code land on the leech lattice, which is a lattice many people are interested in. And then there is, maybe it's a twisted construction. Then there's the orbifold construction of the leash lattice that lands you on the monster CFT, which
You also leash lattice as from a code, because I thought you always get at least C vector of length 2.
That's the other construction.
well, the leash lattice is length 24, so it's C divisible by 8.
No, I mean, it has no vector of length.
Good. So if you do the construction I explained, you're not going to land at the leash lattice, but there's another construction, take this code to another part, another subgroup of these lattices, which gives you the leash lattice. And good that you asked about the goalie code. The goalie code is actually the one they used to in the Voyager mission.
Yeah.
So funding bodies here. This is
I don't need further funding, so I'm going to ask a gravity question. What is what singles out these specific geometries? Like when you have some finite subset of all the possible geometries that contribute, and all the rest just get possible.
You mean why does this infinite sum truncate to a finite number?
So what should we know? Right? Can we learn something about gravity now? Is there some?
Imagine you don't truncate. Then you can divide your sum as the sum over 6 times the sum over infinity over 6 terms, and then you're gonna get an No, that's not true. The sum 1 plus 2 plus 3, that's minus 1 over 12, right? Then you're gonna get the sum 1 plus 1 plus 1, which is actually just infinite. So
if you want pieces that are invariant under
kind of all of this you always should mod out by the infinite volume or infinite sum, but I'm not sure if it's a satisfactory answer, but it's kind of the only way to go from the infinite sum to get something that's actually finite is to only sum over the unique images.
Let me ask the question in a different way. In this older work, this paper with the funny title, The Gravity Dual of the Icing Model, they studied, they used symmetry arguments to do a similar kind of construction, and there the Poincare series truncated to a finite sum of terms, and the reason was a physical reason that these theories have a lot of null states. Now, any chiral CFT had a lot of null states as well, including these. Is there a null state explanation for this truncation or not?
Well, I haven't thought about it. It seems that should explain that you give the answer indeed. So they understood this in this case?
Yeah, I mean, regardless of what one thinks about the actual gravity interpretation of the result, they're able to explain from the spectrum of null states in these theories why the Poincare sum representation of the partition function just collapses down to some finite index subgroup of SL2Z.
That's interesting. Yeah. Yeah, I don't know what to make out of the general statement of that paper though. And it only seems to work with higher genus for Ising and not the other minimal models. Right. But yeah, the story looks very similar. But maybe that has to do with the free Fermat interpretation of these things.
You have the advantage of having a large C version of that story, right?
Yes, exactly. Here we have the average, even if all the members are not listed, the average works at any C.
Can I conclude possibly with a dumb question? It's a very dumb question. So
I'm not sure what the argument is that no longer because it's dumb, but
only because it's dumb.
Yeah, thank you. The gap, C over 36.3.
Yeah.
The best known gap in the Virasoro case is C over 9.08. I'm noticing that 9.08 times 4 is very close to 36. Is this something you've noticed or thought about?
There is this 2 pi e number, right?
So the random case?
Yeah. And if you take this divided by 2, you get very close to 2 pi e. And that we noticed.
Okay.
The origin of this formula is something you can evaluate it to arbitrary precision. It's like it's an inverse value of 1/2 when this is called the entropy function, which is just written in terms of log 2. So this is a known value, and it's just different from 2 pi e. But if you take it over 2, it's quite close to 2 pi e. And it's reasonable to take it over 2 because we actually worked out in our paper a construction of like C comma C bar SU2 theories too. And there you get this number over 2 if C equals C bar. But I don't know if it's reasonable to expect that these two numbers are within, I don't know, 10% of each other or not. Maybe you're too much into numerology if you think that, but maybe good that they're in the same ballpark.
Thanks for entertaining me.
Okay, let's thank Johan again. So you can